All right, in this video, we're going to talk about the integral test, and I'm actually going to split this section into two videos. So in the next video, I'll do the P series. So integral test. In general, it's difficult to find the exact sum of a series like we did with the geometric and the telescoping. All right, so what I need you to understand is it's usually not easy to calculate this. All right, so because of that, in this section and the next few sections, we're going to develop tests to determine whether a series converges or diverges. Okay, and we're going to do that without explicitly finding the sum. Sometimes in these cases, the methods will allow us to get good estimates of the sum, but in other times we won't know anything about the sum, and that's okay. We're really concerned with whether a series converges or diverges, and you'll see why a little bit later. In the second half of our unit in Chapter 9, we will be applying all of these series. So at this point, usually people get frustrated and think, well, why are we doing all this? And we will be using these to help us write Taylor polynomials and Taylor series, which is very useful for integrating complex things. All right, so it is worth it. So let's begin. Integral test. So integral test, this says if we have a function f that is positive, continuous, and decreasing for x is greater than or equal to 1, and if we can write a sequence a sub n, and that's going to be equal to f of n, so the function is going to represent our sequence, then our series, the summation of that a sub n, and the integral from 1 to infinity of that function are either going to both converge or both diverge. Okay, so whatever this integral is going to do, diverge or converge, that's what the series will also do. A mnemonic device for this integral test is please don't calculate integrals. That'll help you remember to check for positive, continuous, and decreasing, and then I is for the integral test. Okay, so let's look at this series. So we're doing the summation of 1 over n squared, and here's a few first few terms of that series. All right, so we're going to use a calculator to fill in this table. If you're using the Inspires, the CASs, you're just going to find that button that has the summation symbol, and it'll have like all these squares by it, right? So you're going to fill in these different values for your n. Okay, so you don't want to put infinity there. You want to put these different values for your n here. Okay, this is going to represent the partial sums. Okay, so you're going to type in n equals 1. You're going to type in our 1 over n squared, but up here is where you're going to be changing all of your upper limits for your summation. Okay, so if we do that, I think when you do the fifth partial sum, you should get something like 1.4636, 1.5498 when you do the 10, and then 50 is 1.6251, 100, I'm getting off already, 1.6350. Let me move this down. All right, the 500 is 1.6429. 1,000 is 1.6439, and then my 5,000 I have to write down here, 1.6447. Okay, so you can see that those partial sums are getting closer and closer to some number around 1.64. Okay, so if you actually do type in the infinity, you do get this number. Okay, so it's about equal to, actually, I think you get pi squared over 6. I don't know what your calculator is going to give you, so check that and see what you get. But the whole idea is the numerical approach is going to give us a good idea. Okay, so are the partial sums convergent? Yeah, so it would appear that way. Okay, so let's look at a geometric approach we're going to draw these inscribed rectangles with a width of 1 and a height equal to the function. All right, so if we do that, I have this first rectangle, that's 1, and then this one's going to be 1/2, and then 1/3, and so on, right? So the height of the rectangle is equal to the area of that. Okay, so as we keep on going, if we kept drawing those rectangles, that would be equal to the summation. Because remember, the series are just, they're equal to these integers. N is equal to these 1, so it's not continuous. Okay. Now, that's the visual geometric approach to the series. Now let's look at the integral test. So can we use the integral test? We have to check for conditions first. Don't try to just do the integral test without checking for that. Otherwise, you'll get some false answer, perhaps. All right, so please don't calculate the integrals. Positive, continuous, decreasing. So is our function 1 over x squared, is it always positive? Well, yeah, if I have x squared, that's always positive. Is it continuous? Yes, there's no discontinuities for x is greater than 1. Now at 0, we have a discontinuity, but remember we're concerned with the integral from 1 to infinity. All right, and then decreasing we can always check by using the first derivative. So our first derivative is going to be negative 2 over x cubed, and that will always be negative. So that's going to be, and keep in mind this is for x is greater than 1. So that's always going to be negative, so that means that our function is decreasing on that interval. Okay, so that means we can use the integral test. And again, you don't necessarily have to show all of that when you do this step, but you do have to check it. Otherwise, like I said, you could be doing the wrong test. Okay, so to find the area of the region using the integral, keep in mind that when I was doing that rectangle, I'll go back here. When we were drawing those rectangles, this first rectangle is not going to be included in the integral, right? Because if I'm doing the area under the curve from 1 to infinity, that's going to do all this space, right? So that's not including this first one. So keep that in mind. All right, so it's not exactly equal. We're not saying that the area under this curve is equal to the sum. That's not what we're saying at all. But what we're saying is that if this converges, then the series will also converge. So just keep that in mind. All right. So that's what this is talking about. We are doing the integral from 1 to infinity of 1 over x squared. So we have to do an improper integral, just like we did in last chapter. So we're going to do the limit as b approaches infinity from 1 to b of x to the negative 2. So the antiderivative is negative x to the negative first. We're going to be plugging in 1 and b. So if I do the limit here, I'm going to be plugging in b here, and if I plug in infinity, that's going to give me a negative 1 over infinity. If I plug in 1, that's a minus a negative 1 over 1. So this part is going to give me 0. This part is going to give me positive 1. So what does that mean? Well, if I can actually find the integral of that, if that gives me a number value, that means that the integral converges. So by the integral test, that means that the series will converge. Okay? So the total area, let's talk about the total area. This is that part with the rectangle that I was just talking about. This integral is not the whole area, right? We were leaving off that first rectangle. So if that integral is equal to 1, right, then we have to add that first rectangle that had an area of 1. So if I had to estimate, this is an estimate of the summation of the series, then that would be true. Now keep in mind, this is not exact, because if we go back again to that rectangle thing, the rectangles are actually smaller. They stay underneath the curve. So this green stuff will be an overestimate of these rectangles. So 2 is actually an overestimate. So we could say, to be a little more exact, that our rectangles are inside the area of the region, so all of that will be less than 2. All right, so that's because we added the 1 and the 1, and we know that was an overestimate. The exact value was pi, this is pi squared over 6. And again, like if you did it on the calculator, we would get that as well. And Leonard Euler was the guy that figured that out. Okay, so that's one example of the integral test. All right, let's consider this example. We have this series n equals 1 to infinity of 1 over the square root of n. Okay, so here's a few of the first terms of that series. Here's what the table suggests. Okay, so if we look at the table, it's a little different than our table before. It's not kind of whittling down to some number. It keeps getting bigger and bigger. So it would appear that this is going to diverge, right? That's what it looks like. So we cannot use that. Just because we have a few terms, we can't just use that as our proof that it diverges. So let's see if we can use the integral test. So f is equal to 1 over the square root of x. So is this positive? Yeah, so if I take the square root of anything that's positive, then that will be positive down in the denominator. So will always be positive, and it will always be continuous for this interval, right? Of course, at 0, there's a discontinuity, but we don't care about that. And then let's see, is it always decreasing? So the first derivative is a negative 1 over 2 square root of x cubed. All right, so remember, these will always be positive numbers here. So this is positive. This will always stay negative then. So yes, we can use the integral test for this example. Okay, so again, graphically speaking, if I draw those rectangles, all right, they're going to be a little bit above the curve for x is greater than 1. So keep that in mind. We're going to do the integral from 1 to infinity of 1 over the square root of x. Okay, so keep in mind we're doing an improper integral, which means we're doing the limit as b approaches infinity. Our antiderivative is going to be 2x to the positive 1/2, and we're going from 1 to b. This is a b. And then if I plug that in, that's going to give me infinity minus 2. Which is infinity. So here's our proof. The integral is divergent, so our series diverges as well. Okay, and then how does the sum of the rectangles compare to the area of the curve? Well, as you can see, these are even larger. So if this integral is diverging, then absolutely these larger rectangles are going to diverge as well. Okay, so keep that in mind too, that the rectangles aren't always underneath the curve. Sometimes they are above the curve. All right, let's look at this third example. Does ln, the series ln of n over n, converge or diverge? So can we use the integral test? Well, let's investigate. Keep in mind, here's just a visual of ln of x. This is not ln of x over x. Okay, this is natural log of x. Okay, so for x is greater than 1, ln of x over x is positive, right? So here's where ln of x starts. So ln of x is positive after x equals 1 and is continuous. So now this last part is f of x decreasing. Okay, so here's our derivative. All right, so make sure that you are doing our quotient rule. So this is x squared, this is x times 1 over x minus ln times 1. So if we simplify that, that's going to be, this is 1 minus ln of x over x squared. This is our first derivative. Now, x squared will always be positive, so we know that's going to be positive right here. Okay, so that would mean that the numerator would have to be negative in order for this to be decreasing. So is this going to be decreasing? Well, it really depends on this value of x, doesn't it? So what we need in order for the first derivative to be negative, we would need ln of x to be greater than 1, right? I need 1 minus something larger than 1 in order for that to be a negative up here. Okay, so we know that ln of e is equal to 1. So if x was equal to e, then that would be equal to 0. And then, so anything larger than e. So if x is larger than e, then we know this will be decreasing. Okay, so here's what throws people off usually. Okay, so again, we care about the divergence, the long end term of what's happening with this integral, right? So it really doesn't matter if it doesn't immediately start at 1. So if it's not decreasing right at x equals 1, that's okay, as long as it eventually happens. So at x equals e, that's when it starts to decrease. Okay, so it's not that big of a deal that the stuff in here is increasing, okay, because we're going to add all, after that, all this decreasing, so it will all eventually converge or do either diverge or converge. So this front part in the beginning won't really matter. Okay, we'll either add it on to some diverging part or we'll add it on to some converging part. Okay, so that's why we don't need to shorten the limits of the integral to be e. So this says e. We don't have to worry about that being e to infinity, okay, because like I said, if we have it diverging or converging, we're just tacking on that extra part. Okay, so you don't have to worry about changing your integral test. All right, so having said that, let's do the integral test. We're going to do the integral from 1 to infinity of ln of x over x dx. All right, so remember, we're going to make ln of x our u. So 1 over x is our du. So that means it's going to be u to the first power. So the antiderivative will be u squared divided by 2. Okay, so here's our antiderivative, and we're evaluating from from 1 to b, or 1 to infinity. So this is going to be 1 times ln of infinity squared minus 1/2 ln of 1 squared. This is 0, right? So I have infinity minus 0. So you can see both the integral and the series will diverge on this one since I'm getting infinity. Okay? So that's our integral test. I'm going to stop this video and do a new video for p-series.